Hello everyone, this is our first video on physics concepts made easier with yours truly, the quantum professor, where we look at physics concepts in the CSEC and CAPE syllabus that we're going to review throughout this series. Right, today we're going to be looking at motion in a straight line. What is motion, and deriving the three equations of motion. So hopefully you enjoy this video. If you do, like, share, subscribe, and leave your comments down below to let us know how you feel about the video. So let's get right into it. So what is motion? Right, so motion is defined as a change in position with respect to time. Right, pretty much a body moving through space and time. Motion can be multidimensional. However, for the CSEC syllabus, we'll be focusing on motion in just one direction, which is the x direction. Right, so here we have a car, right, passing outside as well. Right, so here we have a car moving along the x-axis, going from left to right. Right, so that's pretty much what we'll be focusing on for this video. Right, so to understand motion, we must first get a basic understanding of what position is. So the position of body is pretty much its location in space. This location can be described using the Cartesian plane and the coordinates of the XYZ planes. Right, so we simplify our treatment to the x-plane alone though. Right, so here we have an x-axis going again from left to right, and we have Johnny Go Lucky, right, on the x-axis running from left to right. He's at position x1, and then after some time he's at position x2. Right, so at the beginning of the run, the boy is at position x1. After some time he will have reached position x2. If you want to calculate that change in position, then we can do so by a formula: x2 minus x1 equals delta x. So that's pretty much final position minus initial position, giving us that change in position. Pretty simple. Right, so let's look at some key definitions that we should know if we want to understand fully what motion is. Right, that first definition is displacement. It's defined as a change in position in a specific direction. It's a vector quantity because it takes into consideration direction, and the SI unit is the meter. Distance is pretty much displacement without considering direction. Right, so it's a scalar quantity and it has the same units and symbols as displacement. Velocity now is the rate of change of displacement with respect to time. So velocity is equal to change in displacement divided by the time taking for the change to occur. The SI unit for velocity is the meter per second, ms minus 1. Now acceleration is another step up. It's the rate of change of velocity with respect to time. So acceleration is the change in velocity divided by the time taken for the change to occur. So the SI unit of acceleration will be the meter per second squared, or ms minus 2. So don't get them confused. Velocity is meter per second, which is ms minus 1. Right? Acceleration is the meter per second squared, which is ms minus 2. It should also be noted that velocity without considering direction is called speed. So speed is a scalar equivalent of velocity, just like distance is a scalar equivalent of displacement. So the units of speed is also ms minus 1. Right? So if we look at them in terms of mathematical formula, v is equal to x2 minus x1 over that change in time, which we call delta t. Right? So it's delta x over delta t, or for those of you familiar with mathematical notations, it's dx dt. Right? Which means the same thing as change in x divided by change in t. For acceleration, we have that a is equal to change in velocity over change in time. So it's v minus u over t, where v is our final velocity and u is our initial velocity, and that gives us dv over dt. Again, just change in velocity divided by change in time, or the time taken for the change to occur. Right? So to make use of these definitions in the real world, we pretty much use mathematical formula. For example, if we need to calculate the velocity of a moving body, right, or the average velocity of a moving body, we can apply the formula v average is equal to v plus u over 2. So that's initial velocity plus final velocity divided by 2. Right? So let's look also at our equation for acceleration. Right? See if we can juggle a few things around. We have a is equal to v minus u over t. Final velocity minus initial velocity. Please don't get that confused. It's final velocity minus initial velocity divided by the time taken for the change to occur. So if we fiddle around with this a bit, and we can make v the subject, then we can flesh out our first equation of motion. All right, so we get that at is equal to v minus u, right, and u plus at is equal to v on the next line, and then we flip that around for something that's more familiar, which is v equals u plus a times t. Right, and this is our first equation of motion. Make if you need to understand what's going on here, if you need to catch up, just pause the video, look at it, write it down, make sure that you can do the derivations yourself, make sure that you can do the transposition yourself. So we start from the formula for acceleration, v minus u divided by t, and we make v the subject, right? So we end up with v is equal to u plus a times t. So final velocity is equal to initial velocity plus acceleration multiplied by time. All right, let's move on. Now let's see if we can wrestle up the other two equations of motion. All right, so recall that we had an equation for average velocity, which is final velocity plus initial velocity divided by 2. So if we need to find the distance moved by a body, we can multiply that average velocity by the time taken for the body to complete this motion. So we have s is equal to v average multiplied by time. So it's v plus u divided by 2. And of course, something loud passes. So we have s is equal to v average multiplied by time. So it's v plus u divided by 2, all multiplied by time. All right? But we've just learned a new formula that we're going to use, and it says that v is equal to u plus a times t. So we're going to put this identity for v into our expression for s, and we're going to get s is equal to u plus a times t plus u, right? So all divided by 2, right? If we play around with this a bit, again, something loud passes. If we play around with this a bit, we can flesh out our second equation of motion, right? So next step would be s is equal to 2u plus at over 2, all multiplied by t. So what I've done is just added the u at the beginning plus the u at the end, so we get 2u. So it's s is equal to 2u plus at over 2, all multiplied by t. All right, and then next we multiply through by that t at the top, so it's 2ut plus at squared, again divided by 2. And then next we separate that into two separate fractions, so we get 2ut over 2 plus at squared over 2, right? So finally we have our brand new shiny second equation of motion, s is equal to ut plus at squared over 2, right? And this is our second equation of motion. Again, pause the video, go through the transformations on your own, make sure that you can do all the transpositions by yourself. All right, next up, so on to our third and final equation of motion. We are gonna reuse the same equation that we've had, from the beginning. So we have that displacement is equal to that average velocity multiplied by time. And we're gonna also call on some help from our first equation of motion again, right? So v is equal to u plus at, right? But we're gonna tweak it a bit to make t the subject. So we're gonna get t is equal to v minus u over a. If you have any problems figuring out how we get from v is equal to u plus at to t is equal to v minus u over a, pause the video, make sure that you can go through on your own to make t the subject of that equation, right? So we have t is equal to v minus u over a. So now for a little bit of mathematical magic, we're gonna put this newly formed expression for t into our expression for s that we have up top, and we will get s is equal to v plus u over 2, all in a bracket by itself, which is our average velocity, multiplied by v minus u over a, which again represents t. So I have it in red to make sure that you see that we've replaced t for the expression representing t, which is v minus u over a. All right, so if we write this as one fraction, we can get that s is equal to v plus u times v minus u over 2a. That's one fraction. Now the top part of that is called the difference of two squares, and it conveniently contracts to give us s is equal to v squared minus u squared over 2a. So whenever you have a sum of something multiplied by a difference of the same two things, we get the difference of two squares. So in general, a plus b multiplied by a minus b gives us a squared minus b squared. Or in this case, v plus u times v minus u gives us v squared minus u squared. And we just write about the denominator, which is 2a. Right? Then finally, we fiddle around and adjust to get our final form. And that is that v squared is equal to u squared plus 2as. And this is our third and final equation of motion. Right? So by now, we're all geniuses, we're all Einsteins. We completely understand how to derive the three equations of motion, so we can go to our next physics class and show off, our newfound knowledge. Right? But before we go there, we need to know how to use them in questions. Right? So let's recap. The three equations of motion are: first one, v is equal to u plus at. Second, s is equal to ut plus at squared over 2. And third, v squared is equal to u squared plus 2as. Right? V gives us final velocity, u initial velocity, a acceleration, s displacement or distance, and t time. Right? So let's take a look at a couple examples of how we would use these equations to solve problems. So example 1, we have a car traveling on a highway at 40 meters per second, hits the gas and start accelerating uniformly for 4 seconds until it reaches a velocity of 80 meters per second. Right? So we need to find the acceleration of the car, the distance traveled by the car during acceleration. Right? So the first thing, write down what you're given in the question. We are given that initial velocity u is 40 meters per second. Final velocity is 80 meters per second and the time is 4 seconds. So our solution then must include the formula for acceleration. We're given all the data that's necessary to use this equation. So a is equal to final velocity minus initial velocity over t. So all we need to do is just plug our values into our equation, and boom, we have 80 minus 40 over 4, which is pretty much 40 over 4, so we get 10 meters per second squared. So that means that every second the car's velocity is increasing by 10 meters per second. So if it had gone over to a 5th second accelerating, would have gone up to 90 meters per second, and then on the 6th second it would have gone up to 100 meters per second, and so on. So every second it would have gained a speed of 10 meters per second, right? Which is incidentally the acceleration due to gravity, right? But let's move on to part B. So for part B, we apply the second equation of motion because we're finding distance. So s is equal to ut plus at squared over 2. Again, we have all the information necessary to use this formula because we have u from the question, we have t from the question, and we just found a, right? So we plug our values into our equation and evaluate to give us s is equal to 40 times 4 plus half 10 4 squared, right? That gives us s is equal to 80 plus 80, and finally s is equal to 160 meters. All right, on to our final question. So next, example 2, a fire truck accelerates at a constant rate of 5 meters per second squared from rest for 100 meters. We need to calculate the velocity of the truck after this accelerating period. So again, we write down what we're given. So u is equal to 0 meters per second. That's because we're accelerating from rest. So whenever something is accelerating from rest, the initial velocity is u. Whenever something is decelerating to rest or coming to rest, then the final velocity is 0. Rest means 0 meters per second. Our acceleration is 5 meters per second squared, and s is 100 meters, which is our distance during acceleration. Right? So solution time. Because we have no time given in the question, we are forced to use the third equation of motion, which most students don't like to use because there are squares involved. But we are masters, we are Einsteins, so we can go ahead and use it. Right? So based on the information given, right, again, it's the only suitable one that we can use. So we'll go ahead and just plug our values in and evaluate. So v squared is equal to 0 squared, which is our u squared, plus 2 times 5 times 100. So v squared gives us 1,000. V is the square root of 1,000, which is 31.62 meters per second. Right? Pause the video, make sure that you see what we did here, make sure that you understand and that you can go through on your own and do your own thing, right? Excuse me. So that is the end of our lesson, right? I hope you guys enjoyed it, right? Like, subscribe, leave your comments down below, so let us know what you thought about the video, right? Until next time, have a good one.